Let's do another qualitative example of sketching a wave function for a potential well which will be somewhat lopsided. So I've drawn here a case where there's a potential U1 on the left-hand side of the well, a potential that goes to 0 inside the well, and a potential U2 on the right-hand side of the well. So this might be x equals 0, this might be x equals L, and I'm just implicitly assuming U1 is greater than U2, and I'm thinking about an energy level that's inside or less than both of these two potentials so that the particle is going to be bound. So again, if I have an n equals 1 case, I expect no nodes, and I expect damping outside with a kappa, remember, is always 2m e minus u naught square root over h bar. Now in this case, u naught is a constant, well it's u1 in this case, on the left hand side, and u1 is larger than over here on the right hand side. Excuse me, I've written this backwards. Since u is larger on the left-hand side, I expect this kappa to be larger on the left-hand side, and I expect the damping to be relatively quick. So the n equals 1 case might look like so, and damp out relatively slowly over here, but relatively quickly over there. And as a result, actually, the wave function will be a little bit skewed over to the right. The peak won't be exactly centered because, remember, the first derivative has to be continuous. The n equals 2 case, I expect one node, one place where the wave function goes through 0. Again, I expect that to be a little bit shifted over to the right now. And since the energy is even larger for this particular state, E2 is greater than E1. For the second bound state has a larger energy than the first bound state. I expect this damping to be even quicker in this region and quicker in this region. N equals 3. I always expect n minus 1 nodes, 2 nodes for this case, and the damping should be even that much faster. So this would be the first few wave functions for the bound states of the lopsided potential well.